Let's try to find the complete solution for a one-dimensional conservative system. So for a one-dimensional conservative system, we need to make a few assumptions. One of those assumptions is that the one-dimensional system is being acted upon by a force which only depends on its position. Associated with this force is a certain potential energy, which is going to be given as U as a function of x. And its total energy, which is, or mechanical energy, is a sum of kinetic and potential energies, which are each going to be given by 1/2 mv squared for kinetic and U of x for potential energy. So we can solve for this Vx and come up with this expression right here by moving things around. Note, I am going to get rid of this subscript E total because it's just going to be too much to be writing it again and again and again. So now we're going to do two things. We're going to find this general solution for a position, knowing the velocity vector, for two kinds of systems. One where the particle is being acted upon by a spring force, which is 1/2 kx squared, where the potential is given by 1/2 kx squared. And then the next one is going to be by the virtue of its height, which is the gravitational potential energy, for example, mgh. Okay, so let's begin. So first things first, we are going to solve and try to get that velocity vector in the first place. So what do we have? We have E total equals 1/2 mv squared, which is the kinetic part, plus U as a function of m, which is the potential part. So I'm just going to rearrange it so I want B on one side. This is just going to be E minus U as a function of x. Okay, so I'll keep that for now. Equals 1/2 mv squared, right? This means I can rewrite this as 2 over m E minus U as a function of x equals v squared, or v equals that whole thing. So this is what we have on this page that you see right next to you. 2 over m E total minus U as a function of x will give me my velocity. Awesome. Now I have this. But what am I looking for? I am looking for a general solution for all x's. How do I do that? Well, it's kind of going to be very interesting because I know v can be given by dx over dt, right? It would be easier to solve if this whole thing was as a function of dt. I could move things around and be done. However, it's not going to be that easy because this has this u is the function of x, and so I have to move things around so that I can actually integrate these values. Okay, now comes the interesting part. Once I have this done, I have that expression right here. Now comes my problem of what kind of a system am I looking at. So the first thing I'm going to do is I'm going to look at a system that is dependent on the spring. So now we're going to find the x as a function of t for all systems where the particle is only acted upon by a spring force. So this u is now going to be 1/2 kx squared. Now what do I have to do in order to do that? Okay? So for my spring force, u is going to be 1/2 kx squared. Good? This means that the particle is only acted upon by a spring force. Okay? So I'm going to make a few assumptions, as always. So I'm going to assume that at t equals 0, the particle is at x0 and is at rest. So that means v0 equals 0. Okay? This means that my energy, my total energy from here is going to be, since this is 0, u at x0, which I can rewrite as 1/2 kx naught squared. Okay? Does that make sense? Since it is at rest, v0 equals 0, that means my kinetic energy equals 0, so E total only results in this one. Okay? This I can plug back into here. And this I can plug into here. And what do I get? I get dx over dt is going to be equals to 2 over m square root 1/2 k x naught squared minus 1/2 k x squared. Okay? Excellent. Now I need to move things around, rearrange them. Well, how do I do that? This is a function of x, this is a function of x, this is dx, and this is dt. So what I need to do is do 1 over square root of 2 over m. And while I'm at it, I might as well take these things common out, right? Half k can be taken common out, x naught squared minus x squared. Dx equals dt. So I've just rearranged this, so dt goes on that side, that one comes on this side, so this is going to be rearranged. Half goes away. I can get these out of the brackets, and what do I get? M over k square root, right? I'm going to take these ones out common. 1 over x naught squared minus x squared dx equals dt. Look at it carefully. Is that what we should be getting? Okay, so now that we've done that, can I integrate? Absolutely. So if I take an integral here, I can take another integral here. And I go back to my boundary condition, which says that t equals 0, x equals x naught, and v equals v naught. Okay? So this means my limits of integrations will go from x0 to x and from 0 to t. This side of integration is easy, so I'm just going to get a t here, right? And I'm going to still have an m over k here. This side becomes complicated. So if you remember from your Calc 2 class, what should this integration be? This integration actually is cosine inverse of x over x naught from the limits x0 to x. Okay? When I plug in the limits of integrations, what do I get? M over k cosine inverse of x over x naught minus cosine inverse of x naught over x naught equals t. Cosine inverse of 1. So this one goes to 0 because this is going to be cosine inverse of 1, and cosine inverse of 1 is 0. So this whole thing goes to 0. What do I get? Square root of m over k cosine inverse of x over x naught equals t. Now my main problem was that I need a solution for x as a function of t. So I want this cheese on one side. So what do? I move this over. So it'll be cosine inverse of x over x naught equals square root of k over mt, right? I bring this over to the side. It will be x over x naught equals square, It will now be cosine of square root k over mt, right? Or this could also be written as x as a function of t equals x naught cosine square root k over mt. Does anybody recognize what this kind of looks like? It kind of looks like y equals a cosine of omega t. And what's that expression? It's kind of like a sine wave, isn't it? So a general solution for a spring moving will give you a sine wave, which is naturally what we expect springs to be able to do.